Thank you very much. So I'm here to present CircGR, which is an interactive multi-touch gesture recognition using circular measurements. A little bit of an introduction. So ever since the introduction of the iPhone way back in the early 2007s, multi-touch has become more and more ubiquitous to the point that most users already have an innate sense of what a gesture is supposed to look like, as well as a set of standard gestures which they believe should be supported on all devices. This type of prevalence of such gestures has created an output or an outpour of research into classifiers and recognition techniques for multi-touch. And that gives the illusion that multi-touch is almost a solved problem, as if there's already enough solutions out there, why should we create more? But that is an illusion, because multi-touch still has many issues. Some classifiers work excellent in some domains, not so much in others. For example, they might have great recognition for a gesture when there's where it's symbols, or they have gestures that are specifically online or offline, or for example, if an interface requires multimodal input methods, then recognition doesn't work quite as well. So that was our motivation to create an interactive multi-touch recognizer that provides fast, very fast gesture recognition for non-symbolic gestures, so gestures that don't depend on any particular symbol, specifically for capacitive screens, so touch, there you go. And that's what is CircGR. CircGR is an attempt to provide a solution for very fast gesture recognition. It is a template-based matching algorithm, so it depends on templates and requires as little as one template per gesture. And it focuses, once again, on non-symbolic gestures, so nothing like an A or an arrow, but rather movements like tap, swipes, rotations, and pinch and zooming. To give you a little bit of context where CircGR stands, when it comes to recognizers, you usually have two main approaches to gesture recognition. You usually have a formal gesture recognition language where you define a gesture according to some syntax or some structure. And then if a gesture or an input meets that structure, then it's classified as that. You have examples with XML, JSON, and even regec when it comes to Proton and Proton++. This offers a great ability to define exactly what gesture you want to capture, but a gesture either meets that definition or not. So it can be a little bit tricky getting just the right definition. The other approach is to specify by example, which generally means that you sped up some kind of model, whether it's a hidden Markov model or a finite state machine or some statistical model, even something like a neural network or a machine learning approach. These approaches typically require more training data to establish a model for each particular gesture that you want to recognize. And it also includes classifiers that employ neighbor-like approaches, such as the dollar family, which is a very well-known type of classifier, and it's kind of our inspiration for CircGR. So CircGR falls within the second approach. It's a template-based matcher, which we specify each gesture in our gesture set by one example. All right, so what is that we hope to contribute with this paper and with this work? We want to contribute a linearithmic algorithm for multi-touch gesture recognition with a high accuracy rate, so over 99%, and a Matthews correlation coefficient of 0.95. For those that don't know, Matthews correlation coefficient ranges from -1 to 1, 1 being perfect classification, 0 being no better than random, and -1 being almost completely at odds with the data. We hope that this algorithm also demonstrates early detection of gestures, which means that we detect gestures from the get-go rather from later on in the gesture's execution cycle. And once again, we demonstrate that this one performs with 99% accuracy and 0.86 MCC when it comes to early recognition. We subjected this algorithm to a study with 60 subjects and over 12,000 gestures to evaluate and arrive at these metrics. So let's talk a little about CircGR itself. So the main feature, the main data point that you capture with CircGR is the circular measure, which is the polar angle. The polar angle is just part of the polar coordinate, which represents a unit vector, as shown over here. And a bunch of those angles put together in a set can be averaged out into a resultant vector. So this represents an average of polar angles, and it's usually calculated by the sum of the sines and cosines. These are very, very simple calculations, which is part of the reason why CircGR is as quick as it is. And the last metric that we really use is the circular distance. Circular distance is just the length of the arc between two particular angles. And again, very simple calculation, and whenever I refer to the notion as a circular distance, I'm talking about this. And since our classifier, CircGR, is a nearest neighbor-like template matcher, what establishes some notion of distance, this is the distance that we are talking about. Having known that, you already know everything you need to know to understand it, so it's very, very approachable. All right, so how do we represent a gesture in CircGR? CircGR, a gesture is essentially just two sets of angles. And angles are almost like scalar values. You don't need complicated data structures. You have a set of spatial angles which represent the spatial properties of the gesture and are derived from the input points of those, the input points of the traces that are input. And we have temporal angles which represent the temporal properties of the gesture and are derived from the timestamps of the input points. And both of them together are used in classification. And this is all you need to know to represent a gesture in CircGR. So the process begins by receiving a raw input trace. Again, this is a multi-touch surface. The user is actuating on the surface. We take the multi-touch trace and we interpolate a fixed amount of points. So create from a raw trace of however many points that screen is capturing to a fixed amount of interpolated points, and we generate angles as an angle generated as a vector of equal length between each of those interpolated points. This is how we generate spatial angles in CircGR. And again, it's a very, very simple operation which happens very fast and is done as you're resampling. You might have a possibility that a user inputs a trace which contributes no movement or very little movement, and those traces are labeled as anchors. So we're able to capture traces that move, and we're able to capture traces that do not move, and use them towards recognition. All right. Temporal angle generation is also done at the same time that spatial angles are generated, and they represent moments within the interval of the gesture. The best way to describe it is that you have the start of the gesture and the duration of the gesture, and an angle represents a moment in time of that gesture. If I were to say an angle of pi, I'm talking about roughly halfway in the gesture's interval. And we use this to mark certain points within the gesture as certain events happen within that gesture. And those events come in the form of labels. Now, so each angle is generated by CircGR to assign three labels, to assign a propagation label, a centripetal label, and a clock label. And these labels are tracked across time using the temporal angles. So these are all generated from spatial angles, but they're tracked across time of the gesture with temporal angles. As you can see, this is an example of the propagation level. The propagation label is one of the cardinals or the intercardinal directions, and it's just decided where alpha falls in the sector. If it falls within this sector, it's right. If it falls within the upper sector, it's up. These are arbitrary distinctions. Doesn't matter where you begin looking for these as long as it's consistent throughout recognition. Additional labels are centripetal and clock labels, which once again are generated just as quickly as they're generated from the propagation level to add more sorting and more tracking in terms of what the gesture is doing. So at the end of this entire process, we have a set of angles, and each of those set of angles have a label applied to it that helps us both separate the angles meaningfully and track what the gesture does during the execution of the gesture. So classification follows simply from these processes. We have the input trace is resampled, the angles are generated, and the classification is done via template comparison. As a template matcher, you have an input trace, which is compared to various templates which you have put into the system as what you want to recognize. And the template angles, of course, are compared into the input angles. Angles are compared on labels. So ups are compared with up, down are compared with down. Things that are labeled in or out are compared accordingly. If there are angles that do not match, for example, you have a gesture that goes straight up and a template that goes straight out, then you levy penalties. So part of the reasons we create the labels is to compare angles meaningfully. During these steps, the angles are usually ordered and paired off sequentially, so it's a very simple comparison process, which once again makes it a very fast comparison process, which is why this CircGR has a bottom limit or a fast limit of linearithmic, because it does a comparison, and comparison can only be as fast as a linearithmic time. All right. We evaluated CircGR, as I mentioned, over 60 participants with 12,000 gestures over this gesture set. We gave them this gesture set, and we asked them to articulate it for us on a capacitive touchscreen. Let's see if I can show you guys that. small video to set up. Okay. Okay. This is a bit of how we did the experiment. Now the user forming gestures from that, and then we have a live classification on the side, tracking their moving it. Excellent. At a certain point, you saw a box on the screen. That was to get the user to articulate at different parts of the screen. It didn't have an effect on classification. It was just so that they wouldn't do it at the same point consecutively. Okay. All right, let's resume. Okay, these are the results of our experiment. This is a confusion matrix of all the gestures that we compute. This is, of course, the concentration of values. It's represented on a color scale. As you can see, there's a very large concentration in the diagonal, which of course means that it was very, very, very good classification. Overall, from here we have an accuracy of 99% and a Matthews correlation of 0.95. We wanted to see how the classifier performed during the execution of the gesture. These gestures are captured as a series of windows. So as the user is executing a gesture, it will capture a certain amount of points and classify another certain amount of points and classify another amount. We wanted to see how it performed during each of those windows. Because users did different amount of windows, it was kind of hard to predict which window was going to yield the highest classification rate, and it was also wanted to track if each window was doing at an accepted level. We had to use Cohen's kappa for this. And for all windows, up to 10 windows, we can see that Cohen's kappa does not dip below 0.80. And 0.80 is a very good value for Cohen's kappa. Typically, the range for Cohen's kappa is once again from -1 to 1. 0.4 to 0.75 typically indicates a good agreement, and anything higher than 0.75 typically indicates almost perfect agreement. So we had a very good agreement rate through each window of capture for CircGR. All right. After the experiment, we decided to do a post-hoc evaluation over the data captured in the experiment and compare it to $P, which is another very popular part of the dollar family classifier. And since it was an inspiration for this classifier, we wanted to compare it with that, not only on metrics, but on the amount of time it took to classify all 12,000 gestures and the average time and classify per gesture. As we can see, CircGR has a significantly higher rate of accuracy and MCC. These numbers are actually statistically significant. Even though they're close, they're statistically significant, they're different. The batch time, it took CircGR about almost a little under 4 seconds to classify 12,000 gestures, while it took $P about 125 seconds. That's an order of magnitude of difference. And P-filter is $P with the benefit of filtering templates that don't match on finger amount. So if it was 4 fingers versus 3 fingers, it'd be invalidated completely. And since that's a very trivial addition to make, we added it to $P and called it P-filter. We can see that it sped it up quite a lot, but not nearly as much. On a per gesture time, CircGR can classify a gesture on average less than 1 millisecond compared to P-filter, which is about 3.2 milliseconds, and $P, which is about 19 milliseconds. So in a real-time application context, CircGR would be very good because it's a very, 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 very quick classification. I talked about early detection. This is a picturized version of early detection. As we have time, we know that the amount of points is constantly increasing as the user enters more and more points. And here you can see the different windows being captured. We wanted to evaluate how accurate it was just at the first window, not after the user's been actuating for a while, but just as the first window. And at the first window, once again, we got an accuracy of 99%. And a Matthews correlation coefficient of 0.86. A little bit lower, but still great. And this is at a window of 64 points, which is generated very quickly in modern touchscreens. Our future work would imply not only applying this algorithm to applications that involve navigation in 3D environments, but also expanding this work to three-dimensional context, as well as improving the early detection aspects of this algorithm. A future study may evaluate the degradation of accuracy in CircGR when we omit sorting. During classification, we sort angles so that we can compare them more effectively. If we skip that step, it becomes a linear classifier instead of a linearithmic classifier. So we want to investigate what happens when we do that at an experiment level. All the material is available at circgr.com. The code, the paper, the appendix, and even the video. We have the data set available for our experiment, and we will be having a demo today and tomorrow if you want to go see it. And any questions?
Time for one or two short questions. Is there any? Okay, if not, you can think about it. I have one question for you. You had your angular bins in 8 sections, right? Up, left, right, and so on and so forth. Those yeah, so how did you choose them, and did you evaluate the effects of other angular binning schemes?
Can you repeat the question?
So you had your angular bins, right, for your on one slide, where you classify.
Right. Since this isn't a two-dimensional surface, up, down, left, and right are relative.
You had these eight.
Yes,
bins,
eight in cardinal direction.
Did you evaluate other amounts of bins? Did you evaluate other binning amounts, other amounts of bins?
We did not, because we felt that 8 was. It was working empirically. We observed that it was working. So we haven't subdivided that further. The point of labels, such as up, down, left, or right, is to group angles significantly, right? And to group them meaningfully. The labels themselves are arbitrary, really.
I'm aware of that. Yeah, but I meant the number of labels. Okay, so but you didn't.
Okay.
And it was working fine. So
yeah, it was working fine. So empirically, we decided not to add more because it was working fine. Yes.
Okay, thank you so much.
Okay,
there we have one, or maybe one short question.
Set up and maybe it connects to repeating things. If you remove those categories, your recognizer would be.
I'm sorry, you're gonna have to speak up a little bit because I'm a.
If you remove those bin categories, would it be recognizer would be rotational invariant? It would recognize the gesture as starting here or starting over there.
Sorry, please speak up a little bit. Okay. Thank you.
So if you remove those bins that you have vertical, horizontal, and all that, because those are absolute in space. And something nice that your algorithm has is that once you compute the angle, you compute the difference in angle to the next one, and the difference in angle to the next one. So if you remove that, it could be rotational invariant, right? You could start the gesture, my rotation gesture here, or I could start it here and do it over there. Is that?
Are you talking about the labels as well?
So
yeah, it would become rotational invariant in that it really tests that as well.
And the follow-up would be, would it be possible to actually have these labels related to the initial orientation that you have in the first segment? Because my up could be dependent on where I start, my direction in which I start. Because that would be another way of still keeping your labels and having it rotational